The Central Processing Unit CPU, often known as the brain of the computer, is an essential component responsible for executing instructions from programs and performing data processing tasks. The CPU is crucial in every computational operation, from basic arithmetic calculations to complex algorithms, and plays a key role in determining the overall speed and efficiency of a computer. Key components of the CPU. Arithmetic Logic Unit, ALU. The ALU is responsible for performing all arithmetic and logical operations within the CPU. Arithmetic operations include basic mathematical functions like addition, subtraction, multiplication, and division. Logical operations involve comparisons such as greater than, less than, or equal to and bitwise operations. The ALU is essential in enabling the CPU to make decisions based on the data it processes. Control Unit CU. The CU manages and directs the operations within the CPU. It interprets instructions from computer programs, directs the data flow between the CPU and other parts of the computer, and synchronizes the execution of instructions in the correct order. By controlling the communication between the CPU and memory, the CU ensures that the CPU operates smoothly and efficiently. Registers. Registers are small, high-speed storage locations within the CPU that temporarily hold data and instructions while they are being processed. Different types of registers serve various purposes. Data registers hold data that needs to be processed or is in the middle of a calculation. Address registers store memory addresses for data locations, allowing the CPU to quickly access and retrieve information. Instruction registers store the instructions currently being executed by the CPU. Registers facilitate quick data access and improve processing speed by reducing the need to constantly access the main memory. Cache memory. Cache is a small, high-speed memory that stores frequently accessed data and instructions. It is closer to the CPU than the main RAM, allowing the CPU to retrieve commonly used data quickly, which minimizes latency. Cache is usually divided into levels. L1 cache, the smallest but fastest cache, located closest to the CPU cores. L2 cache, larger than L1 but slightly slower, often shared between cores. L3 cache, the largest and slowest cache, shared among all CPU cores, and used to store data that is not as frequently accessed as that in L1 or L2. Clock speed and clock cycle. The CPU operates based on a timing signal, called the clock cycle, which measures the number of operations the CPU can perform per second. Clock speed, measured in GHz GHz, determines the number of cycles per second. Higher clock speeds mean the CPU can execute instructions faster, which generally improves performance. However, high clock speeds can increase heat production, requiring better cooling solutions. Random access memory RAM is a crucial component in a computer system, serving as the system's short-term memory. It temporarily stores data and instructions that the CPU needs to access quickly, enabling fast read and write operations that enhance system performance. Unlike storage memory, such as hard drives or SSDs, RAM is volatile, meaning its contents are lost when the system powers down. Key features of RAM. Volatility. RAM is a volatile memory type, meaning that it requires power to retain data. When the computer is turned off, all data in RAM is lost. Random access. Unlike other storage types like hard drives or SSDs, RAM allows data to be accessed in any order randomly, which provides much faster read-write speeds since the CPU can directly access any part of the memory. Temporary storage. RAM is used for temporarily holding data that the CPU actively processes, such as open applications, operating system functions, and active files. This short-term storage is what enables quick data access. Capacity and speed. RAM capacity is typically measured in gigabyte, with speeds measured in megahertz or gigahertz GHz. The more RAM a system has, the more applications it can handle at once without slowing down. The higher the speed, the faster the data can be read from or written to the memory. Types of RAM. DRAM. Dynamic RAM. DRAM stores data in tiny capacitors that need to be refreshed continuously to retain data. It's the standard type of RAM found in most computers. SRAM. Static RAM. SRAM doesn't need constant refreshing, which makes it faster than DRAM, but it is more expensive and takes up more space. It's commonly used in smaller quantities for CPU caches L1, L2, and L3 caches. SDRAM. Synchronous DRAM. SDRAM synchronizes with the CPU's clock speed, which makes it faster than traditional DRAM as it can perform tasks in sync with the CPU's operations. DDR-SDRAM Double Data Rate SDRAM. DDR-SDRAM is an advanced type of SDRAM that transfers data twice per clock cycle, effectively doubling the data throughput. Subsequent versions DDR2, DDR3, DDR4, and DDR5 have progressively higher speeds and efficiencies, with DDR5 being the latest standard. GDDR Graphics DDR. GDDR, for example, GDDR5, GDDR6 is a specialized type of RAM used primarily in graphics cards, optimized for the high throughput needs of rendering images and video. Storage is an essential part of a computer, responsible for holding data permanently, including the operating system, applications, and user files. Unlike RAM, storage is non-volatile, meaning it retains data even when the computer is turned off. There are two main types of storage devices: hard disk drives HDDs and solid-state drives SSDs. Hard disk drives HDDs. An HDD is a traditional storage device that uses mechanical spinning disks, or platters, and a read-write arm to store and retrieve data. How HDDs work. Platters. Data is written on spinning magnetic disk platters inside the hard drive. Read-write arm. The arm, equipped with a magnetic head, moves across the platters to read or write data. RPM revolutions per minute. The speed of the spinning platters measured in RPM impacts the drive's read-write speed. Common RPM rates are 5,400 or 7,200 RPM, with higher RPM offering better performance. Advantages of HDDs. Cost-effective. HDDs offer a large amount of storage at a lower cost per gigabyte compared to SSDs. Higher capacity, available in larger sizes up to 2 OTB or more, making them suitable for storing large amounts of data affordably. Disadvantages of HDDs. Slower speeds. HDDs are slower than SSDs because of their mechanical parts, which affect data retrieval times. More prone to damage. The moving parts make HDDs more susceptible to physical damage or wear over time. Higher power consumption. HDDs consume more power and generate more heat due to their mechanical nature. Solid-state drives SSDs. An SSD is a newer type of storage device that uses NAND-based flash memory, similar to the technology in USB drives, to store data. How SSDs work. Flash memory. SSDs use interconnected flash memory chips to store data, enabling faster access. No moving parts. Unlike HDDs, SSDs have no moving components, which makes them faster, quieter, and more durable. Types of SSDs. SATA SSDs. These connect through the same SATA interface as HDDs and offer speeds of up to 600 megabytes per second. While faster than HDDs, they are limited by the SATA connection. NVMe SSDs. NVMe non-volatile memory express SSDs connect via PCIe slots, providing significantly faster data transfer speeds up to 7,000 megabytes, yes or more, making them ideal for high-performance tasks like gaming or video editing. Advantages of SSDs. Speed. SSDs are much faster than HDDs in both read and write operations, significantly improving boot times and application load speeds. Durability. With no moving parts, SSDs are less prone to physical damage and can withstand more shock and vibration. Energy efficiency. SSDs consume less power than HDDs, making them ideal for laptops and other portable devices. Disadvantages of SSDs. Cost. SSDs are more expensive per gigabyte than HDDs, especially at higher storage capacities. Limited write cycles. Flash memory has a finite number of write cycles, which can affect the lifespan of SSDs, though modern wear leveling technologies help mitigate this. The motherboard is the main circuit board of a computer, acting as the central hub that connects all components and allows them to communicate. It holds the CPU central processing unit, RAM random access memory, storage drives, power connectors, and various other components. Additionally, it contains the chipset and other circuits responsible for data flow and power distribution across the computer. Key components of a motherboard. CPU socket. The CPU socket is where the processor is installed. Different sockets support different types of CPUs, meaning the motherboard must match the CPU type. The CPU socket provides power to the CPU and connects it to other components through the chipset. Chipset. The chipset controls data flow between the CPU, memory, storage, and other peripherals. The chipset is typically divided into two main parts. North bridge. Handles high-speed communication between the CPU, RAM, and graphics card. Southbridge manages communication with slower devices like hard drives, USB ports, and other peripherals. Your motherboards have merged these into a single unit, often just referred to as the chipset. Memory slots. DIMM slots. The memory slots hold RAM sticks. Most modern motherboards have between 2 and 8 slots, depending on the form factor and intended use. These slots connect the CPU to the RAM, allowing fast access to data during operation. Storage connectors. SATA ports. These ports connect storage devices like HD disks, SSDs, and optical drives. They are slower than newer NVMe connectors but are widely used. Two slots. Two slots are used for high-speed SSDs, often NVMe SSDs, offering significantly faster data transfer rates than SATA ports. PCI slots. PCI peripheral component interconnect express slots allow expansion cards like graphics cards, GPUs, sound cards, network cards, and other peripherals to connect to the motherboard. There are different sizes of PCIe slots, including X1, X4, X8, and X16, with X16 commonly used for GPUs. Power connectors. The motherboard has multiple power connectors, including 24-pin ATX connector, main power supply for the motherboard. 8-pin or 4-pin CPU connector supplies power to the CPU. SATA power connectors provide power to storage devices. BIOS UEFI firmware. BIOS Basic Input-Output System, or UEFI Unified Extensible Firmware Interface, is firmware stored on a chip on the motherboard, enabling the system to boot and initialize hardware components. UEFI is the modern replacement for BIOS and offers faster boot times, support for larger drives, and a graphical user interface. I/O ports and headers. The rear panel of the motherboard contains I/O input-output ports for connecting peripherals such as USB devices, audio devices, network cables, and display monitors. USB headers. Internal connectors for USB ports on the front of the case. Audio headers. Internal connections for the computer's audio system. The power supply unit. PSU is a crucial component in a computer, responsible for converting electrical power from an outlet into usable power for the computer's internal components. It converts alternating current AC from the wall socket into low-voltage direct current DC, which is then distributed to the CPU, GPU, hard drives, motherboard, and other components. The PSU ensures each part of the computer receives the proper voltage and current, protecting components from power fluctuations and overloads. Key functions of the PSU. Power conversion. The PSU converts high-voltage AC power, typically 120 volts or 240 volts, to low-voltage DC power suitable for the computer's components. Common DC outputs from a PSU include 12 volts, 5 volts, and 3.3 volts. Power distribution. A PSU distributes power to different components through various connectors. 24-pin ATX connector, main power for the motherboard. 4-pin or 8-pin CPU connector, supplies power specifically to the CPU. PCI connectors, power for the graphics card GPU. SATA Molex connectors, power for storage devices like SSDs, HD disks, and other peripherals. Power protection. Most modern PSUs include protection features to guard against issues like overvoltage, undervoltage, overcurrent, and short circuits. These protections prevent damage to sensitive components if the power flow is interrupted or irregular. Cooling. PSUs usually contain built-in fans to regulate their temperature and prevent overheating. This helps maintain efficiency and extends the PSU's life by keeping components cool. PSU ratings and efficiency. Wattage. The PSU's power output is measured in watts W, indicating how much power it can supply. A higher wattage rating means the PSU can support more power-hungry components. Common PSU wattages range from 400 W for basic systems to 1200 West or more for high-performance gaming and workstation computers. Efficiency rating. Efficiency is crucial for a PSU because it determines how much of the input power is converted into usable output. Power without excessive waste heat. PSU efficiency is rated through the 80+ certification, with levels including bronze, silver, gold, platinum, and titanium. Higher ratings indicate greater energy efficiency, meaning less power is wasted as heat. Modularity. Modular PSUs allow users to connect only the cables they need, reducing cable clutter and improving airflow. Semi-modular PSUs have some permanently attached cables, typically the main power connectors, and offer optional connectors for other devices. Non-modular PSUs have all cables attached permanently, which can lead to more cable management requirements. Graphics Processing Unit GPU, also known as a graphics card or video card, is a specialized processor designed to accelerate the rendering of images, videos, and animations for display. While CPUs handle a broad range of tasks, GPUs are optimized for parallel processing, allowing them to perform thousands of calculations simultaneously. This makes GPUs essential for graphics-intensive applications like gaming, video editing, 3D rendering, and, more recently, for scientific computing and artificial intelligence tasks. Key functions of the GPU. Rendering graphics. The primary role of a GPU is to render complex graphics efficiently. It processes data to create high-quality visuals, calculating colors, textures, shading, and geometry. This allows for realistic and immersive environments in games and simulations. Parallel processing. GPUs have hundreds or thousands of smaller cores, optimized for performing multiple calculations at once, making them much faster than CPUs in specific tasks. This parallel architecture is particularly useful in applications requiring massive amounts of data to be processed simultaneously, such as machine learning and cryptocurrency mining. 3D graphics and effects. GPUs calculate advanced visual effects like lighting, shadows, and reflections. These effects are essential for creating realism in games and professional design software, where they simulate how light interacts with objects and materials. Artificial intelligence and data science. Modern GPUs, especially those from NVIDIA and AMD, are used extensively in AI and data science for tasks like deep learning, neural networks, and big data analysis. GPUs can handle large datasets and perform complex computations faster, enabling breakthroughs in AI-driven applications. Video encoding and decoding. Many GPUs have dedicated video encoders and decoders, often referred to as hardware-accelerated codecs, which help compress and decompress video files. This allows smoother playback of high-resolution videos and faster video rendering for content creation. Components of a GPU. Graphics core. The heart of the GPU, the graphics core, includes hundreds or thousands of cores that process graphics instructions simultaneously. The more cores a GPU has, the more capable it is of handling complex graphics and compute tasks. VRAM. Video RAM. VRAM is dedicated memory on the GPU, storing textures, frame buffers, and other data needed for rendering. Modern GPUs have VRAM sizes ranging from 4 GB to 24 GB or more, with higher VRAM benefiting high-resolution gaming, professional 3D rendering, and AI tasks. Cooling system. Due to the intense processing, GPUs generate significant heat and require cooling systems, which may include fans, heat sinks, or even liquid cooling for high-performance GPUs. Efficient cooling ensures stability and prolongs the GPU's life by preventing overheating. Cooling system is crucial for maintaining the optimal temperature of computer components, especially those that generate significant heat, such as the CPU Central Processing Unit, GPU Graphics Processing Unit, and Power Supply Unit PSU. Effective cooling prevents overheating, which can reduce performance, cause system instability, and even lead to hardware failure. Key types of cooling systems. Air cooling. Air cooling is the most common method of cooling in computers. It uses fans and heat sinks to dissipate heat from components. Heat sinks, made of metal, often aluminum or copper with a large surface area. These are placed directly on top of the CPU or GPU to absorb and transfer heat away from the component. Fans then blow air over the heatsink, moving the hot air away from the component and cooling it down. Case fans also help by circulating air inside the computer case, drawing cool air in and pushing hot air out. Liquid cooling. Water cooling. Liquid cooling is a more efficient but complex system, often used for high-performance or overclocked PCs that generate more heat. Liquid cooling loop. Liquid cooling involves a loop containing a liquid coolant, often water mixed with anti-corrosive agents. The liquid flows through water blocks attached to heat-generating components, absorbing heat. Radiator and fans. The heated liquid then moves to a radiator, where it is cooled by fans before being recirculated back into the loop. This system allows more effective cooling as liquid transfers heat faster than air. Hybrid cooling. Hybrid cooling combines elements of both air and liquid cooling for enhanced cooling efficiency. For example, Some GPUs use liquid cooling for the main chip with fans to keep the RAM and other components cool. Passive cooling. Passive cooling uses heat sinks and natural convection without fans, relying solely on material design and airflow. This method is often used in low-power devices, laptops, or systems where silent operation is essential. However, it's not suitable for high-performance components that produce a lot of heat. Key components of a cooling system. Heatsink, a metal block often with fins that absorbs heat from the CPU or GPU and transfers it to the air or liquid cooling system for dispersion. Thermal paste, applied between the CPU, GPU and the heatsink. Thermal paste fills in microscopic gaps, improving heat transfer efficiency between the component and the heatsink. Fans. Fans are used throughout the cooling system. CPU fans attached to heatsinks, case fans circulate air within the case, and exhaust fans expel hot air from the case. Radiators. In liquid cooling systems, radiators are where the coolant dissipates the heat it has collected. They are usually attached to fans that help in cooling down the coolant. Input devices are hardware components that allow users to interact with a computer by sending data, commands, and signals for processing. These devices convert user actions into digital signals that the computer can interpret and respond to. Below are some common input devices. 1. Keyboard. A keyboard is the most traditional input device, allowing users to type letters, numbers, and symbols. Keyboards can come in various layouts such as QWERTY, AZERTY, and can be mechanical, membrane, or virtual on-screen keyboards. Special function keys. Most keyboards include function keys F1, F12, arrow keys, and other specialized keys for shortcuts and commands. 2. Mouse. A mouse is a pointing device that lets users interact with graphical elements on a screen. Movement is detected through optical sensors or a laser. Buttons. Typically has left, right, and middle scroll buttons for clicking and selecting. Types: optical, laser, trackball, and wireless mice. 3. Touchpad. Commonly found on laptops, a touchpad is a flat surface that senses finger movement, allowing users to control the cursor without a separate mouse. Multi-touch support. Many touchpads support gestures for scrolling, zooming, and other actions. 4. Trackball. A trackball has a stationary ball that users rotate to control the cursor. It is often used in specialized equipment and for accessibility reasons. 5. Scanner. A scanner digitizes physical documents or images, turning them into digital files. Types: flatbed scanners, sheet-fed scanners, and handheld scanners are common variations. 6. Microphone. A microphone captures audio input, allowing users to record sound or give voice commands. Uses: commonly used in video calls, gaming, and voice recognition software. 7. Joystick and game controller. Joysticks and game controllers are used for gaming, providing physical input for in-game navigation and actions. Varieties include features like analog sticks, buttons, and triggers for various gaming consoles and computers. 8. Graphics tablet digitizer. A graphics tablet is a device that allows artists and designers to draw or write with a stylus. It converts strokes into digital signals, making it ideal for digital art and design. Pressure sensitivity. Many graphics tablets detect pressure, allowing for more precise control. Output devices are hardware components that take processed data from a computer and convert it into a form understandable to the user, such as visual, audio, or physical output. These devices allow users to perceive and interact with the information generated by the computer. Common output devices. Monitor. The most common output device, a monitor displays visual information, including images, videos, and text. Monitors use various display technologies like LCD, LED, OLED, and more recently, mini LED and micro LED. Types: CRT, LCD, LED, OLED, curved, and touchscreen monitors. Resolution. Monitors vary in resolution, from HD 720p to 4000 and even 8K for ultra-high definition displays. Printer. Printers produce a physical copy of digital documents, images, or other computer-generated data. Types: inkjet printers, ideal for color and photo printing, use liquid ink. Laser printers, good for high-speed and high-volume printing, use toner powder. Dot matrix printers, often used for receipt printing, create output by impact. 3D printers, produce three-dimensional objects by layering materials based on digital designs. Use cases: common in offices, schools, and homes, with specialized models for photo, industrial, and 3D printing. Speakers. Speakers convert audio data into sound, allowing users to listen to music, videos, and system sounds. Types: built-in laptop or monitor speakers, desktop speakers, and surround sound systems. Features: ranges from basic two-speaker setups to advanced surround sound systems with subwoofers for enhanced bass, headphones, and earbuds. Personal audio devices that allow users to hear audio output without disturbing others. Often used for private listening in gaming, music, and online meetings. Types: wired, wireless, over-ear, in-ear, and noise-canceling headphones. Projector. Projectors display computer output on large screens or surfaces, ideal for presentations, classrooms, and home theaters. Plotter. Plotters produce high-precision drawings on paper or other materials and are primarily used for engineering, architectural designs, and large-scale graphics. Types: pen plotters, electrostatic plotters, and inkjet plotters. Functionality: unlike printers, plotters can draw continuous lines, making them ideal for detailed and large-format technical drawings.